All right, we're back. We are about to talk about the different forms that an amino acid takes based on the pH of the solution in which it is present. All right, so the things to be aware of, right? The amino acids have two functional groups, and their acid-base properties are pretty different from each other. In particular, the carboxylic acids have low pKa's. They average, when you take all 20 amino acids and you average out all the pKa's of the carboxylic acid unit, it ends up being about 2.18 values for the pKa. And the standard deviation of all 20 is plus or minus 0.23. On the other hand, your amino group has an average pK of 9.42 for all 20 amino acids, and the standard deviation is a little bit larger. It's a 0.44 standard deviation. So yeah, you're definitely on the higher end of the pH scale. So what this basically means is that when you are thinking about, okay, what's the amino acid doing in terms of its acid-base chemistry, as you change the pH of a solution, what you got to remember is that in water, which is usually where you're going to be dealing with amino acids, you have a pH range of 0 to 14. But when you look at this section, right, and assuming that these are the only two components that have acidic protons, then basically this breaks down into three regions. You have region A, where you're the lowest pH, and you go up to the pK value. In reality, a little bit higher than that, but you reach that pK value, the first pK value, and that ultimately signifies the pH at which you start losing the first acidic proton, the carboxylic acid proton, to be most exact. Then you get into region B, which from pK1 up to pK2, nothing really happens in terms of deprotonation. But once you hit that second pK, you start seeing substantial deprotonation of the amine group, and then you get to a final state, basically region C. So your amino acids, as far as how they actually are, appearance-wise, in the most acidic scenario, all the amine groups are protonated, and what that also means is that the amine groups are cationic. On the other hand, although the carboxylic acids are also protonated, they only yield a neutral species. The protonated carbonyl or carboxylate group is neutral. The protonated amine group is cationic, and that's what you're going to have to remember to make sense of this ordeal right here, because as we start increasing the pH, we're making the solution more basic. And once you go past the value of the pKa, you're going to start deprotonating that proton. So the proton of the carboxylic acid will come off once you make it past the first pKa. And so now the identity of your amino acid is going to be one in which you have an ammonium um, group as well as a carboxylate group. But if you keep increasing the pH so that you go past the second pK value, well, at that point, the amino group will be deprotonated, and now that will be neutral. So what you can see right here is that in region A, the overall charge of the amino acid is +1. In region B, the overall charge of the amino acid is 0 or neutral. And in region C, the charge of the amino acid is -1. So you're basically decreasing the charge by 1 unit as you go past each of the pK values. Now, the one where we have neutral charge, this is also referred to as a sweeter ion. You may recall that terminology from where we talked about ylids in the Vedic reagent, chapter of aldehyde and ketone chemistry. So that's the same thing here. We have a molecule that has charges, but the charges completely cancel each other out. All right, now to fully make sense of this, you can refer to a titration curve. If you were to titrate this amino acid, what this will basically look like is that at the mid equivalence point, you will have a pH that equates to the first pK value. But just like the name implies, this is only halfway through the the actual process of deprotonation. So you still have half of the original amount of the fully protonated form of the amino acid, the one where you have a +1 charge. But once you get to the inflection section of the titration and you reach the inflection point itself, that's when you will have transformed all of A completely into B. And B is our sweeter ion, right? It's our neutral species. When we go past that, eventually we will hit the second mid equivalence point, which pH corresponds to the pK value of the second most acidic proton. So in essence, what we're basically saying is that the pH, when you get entirely 100% of the neutral species, is equidistant from the pH of the first mid equivalence point and the pH at the second mid equivalence point. So another way to say that is that the pH at the first equivalence point, where you have 100% of the neutral species, is going to simply be the average. And by the way, this should be a plus, so just be careful there. So it's going to be the average of pK1 and pK2. So add those two things together, divide them by 2. That will give you the true value. And we have a term for it. We call this the PI, also referred to as the isoelectric point. And in the case of this particular situation, we'll simply just add the value of pK2 and pK1 together, divide them by 2. All right, now with that said, I wanted to highlight a few amino acids that kind of have some worthy discrepancies, just like the title describes. Okay, and for this to make sense, I'm going to show you the range of pKa values, including the standard deviation. So I took the average and I said, okay, subtract the standard deviation from it, and that gave me this lower value of 8.98 for the amine group. I took the average value and then I added the standard deviation, which gave me a value of 9.86. So this is the range where the majority of the amino acids tend to have its pK value for the amine group. And for the carboxylic acid group, similarly, I did the same thing. I subtracted the standard deviation from the mean. I added the standard deviation to the mean. And then this gave me this range, which applies to the majority of the amino acids on the list. Okay, that said, there are some interesting deviations. So, for instance, when you look at the pKa of the amine group of proline, we see that pKa is substantially higher than the range that we have here. It happens to be 10.6 as opposed to staying in the nines. And the reason for that is because we are dealing with a secondary amine as opposed to a primary amine. And that alone increases the basicity of the nitrogen, which makes this thing increase in value. All right. Then another amino acid that we have that has a discrepancy happens to be cysteine. And this one is kind of interesting because the value for the amine group is 10.28, whereas we're looking at 9 mostly for the majority of amino acids. And now the reason for this is because of the pKs of the other two acidic protons. You have the carboxylic acid, which is going to be lower by default, but then the sulfur hydrogen bond is also acidic enough that gets involved. So pretty much you don't actually hit the deprotonation of the amine group until these two have been removed. And once that happens, you have a 2 minus charge from those two groups and a +1 charge from the amine group, right? So basically, if you were to deprotonate this amine group, you will make a dianion, which will be, kind of a high negative charge for a molecule. So that's kind of what's preventing this thing from being any more acidic than it is. Okay, the next one is lysine, and fortunately, I don't have a whole lot to say about this one. But what I wanted to point out is that um, this is almost within the range, so take it with a grain of salt, but it's a little bit low compared to the majority of the amino acids on the list. And this may just be as a result that the deprotonation um, of that amine group will make the sweeter ion directly. Um, the side chain happens to be more basic than the amine group itself. But I think we're drawing straws at this point in terms of the explanation. The next amino acid is asparagine. And the interesting thing about this is that we also have a low value for the pKa of the amine group. As a result of the structural motif of the side chain, the same thing happens to another amino acid, but let me show you here first things first. Because of the amide functionality here, you have a resonance structure that gives you an oxo group, an oxo anion, which is perfectly situated next to that NH bond. And that interaction, the hydrogen bonding interaction, ultimately allows for that bond to be more acidic, to be weaker. All right, two more to go. So histidine, the carboxylic acid group is actually, pretty low compared to the average that we have right here, including standard deviation, right? And the same thing happens to aspartic acid. We have a low value compared to the range up here. And the main reason for that is because, structurally speaking, if you count the number of carbons and nitrogens or oxygens, that gets us pretty close to that OH bond there to also be engaging hydrogen bonding, which does weaken that OH bond and makes it more acidic. So, some interesting features to point out. Now, this one is definitely a big anomaly, and I haven't really found a good way of explaining this one. Even what I'm about to tell you is not really great. But the carboxylic acid group of phenylalanine has the lowest pK value for the carboxylic acid, and compared to the rest of the amino acids, and yet the amino acid chain is totally hydrophobic. Um, so the only thing you can kind of say about it is like, well, once you deprotonate the carboxylic acid, this becomes neutral. The hydrophobic chain probably doesn't want to have charges around. But then again, you could say that about any other hydrophobic amino acid, or amino acid with hydrophobic chains. Um, so one thing that could be involved here is that it may help out to have a neutral species when this amino acid is interacting with itself, trying to form kind of a crystal pattern of some sort. But most of what I found online wasn't really all that helpful in terms of determining if this is true or not. But the fact that this pK is so low kind of points out that, yeah, something interesting is happening on the periphery. All right, so a couple of things I want to show just to kind of finalize this video in regards to the side chains. I already talked about cysteine as being one of the side chains present in there. And the idea right here is that the acidity of the SH bond is substantially lower than what you expect for other things, definitely lower than what you have for the alcohol derivative. And that's simply because the SH bond is a longer bond. The longer the bonds get, the more acidic the compound becomes. The same thing is true for HCl, HBr, HI. Another one that's also noteworthy is tyrosine. The pKa of that side chain is 10.07. And that's simply because of the fact that you have a hydroxyl group attached to an aromatic ring. So resonance effects get involved, hybridization effects get involved, and they both allow electron density to be withdrawn away from that oxygen. All right. After that, we have good old aspartic acid, which has a pK in tandem with most regular carboxylic acids. Now the interesting thing here that I want to highlight is that the carboxylic acid of the amino acid regular chain is lower than the carboxylic acid pK of the side chain, and that's because this carboxylic acid in red is closer to the ammonium group compared to the side chain itself. And not only that, but if you extend the carboxylic acid chain by going from aspartic acid to glutamic acid, you see an increase in that pK because now you're further away from that ammonium group. And so the electron withdrawing effect is diminished. All right, now histidine, we also have a low value for the actual pK of that side chain, mostly because of the fact that when you protonate it, you protonate the nitrogen that has the lone pair right here. And that nitrogen is an sp2 hybridized nitrogen. So you have more acidity associated with that hybridization. You lower the pK as a result of that. All right. Um, Lysine has a pK that is actually pretty high, and we mentioned that just a few minutes ago on a previous slide. So this thing, yeah, it's up there in terms of basicity. And compared to the previous one, you're talking about an sp3 hybridized nitrogen. So you're kind of just talking about a regular amine altogether. But compare that to arginine, which has this guanidinium chain. This has the highest pK out of all the different side chains and all the amino acids, period, because you have resonance uh, engaged thoroughly in this side chain via electron donation. And then that allows you to ultimately make this proton really get stuck on the nitrogen as a result of increasing the electron density right about that NH group. All right, so with that said, we're going to stop the video right here. And on the next one, I'm going to show you, how you go about calculating the isoelectric points for these amino acids that have side chains that actually have um, active, protons that can be deprotonated in your basic, and acidic media in water. So I'll catch you in that video. Bye-bye.